Good morning. Today we would like to present our research of single bubble sonoluminescence. So what is sonoluminescence? Sonoluminescence is a phenomenon where a bubble suspended in a liquid and exposed to intense acoustic fields emits light. On the slide, you can see a white dot, if you can. And so this is the glow of bubble. And this is a little bit brighter one. Our aims were to obtain this phenomenon experimentally, investigate it qualitatively, and if it is possible, quantitatively, determine the conditions for the appearance of the bubble glow, and to measure the bubble spectrum, if it would possible, at different temperatures of the water. In our presentation, we would at first describe our theoretical model, then we talk a little about our experimental setup, then show our results and discussion. So our theoretical model, there are several theoretical models that pretend to explain this phenomenon, but we stopped on the hotspot model, which explains the bubbles glow by a high temperature of this bubble, because it has very rapid compression. So this theory based on the Rayleigh-Placid equation that you can see on the slide. The first term is for acceleration of the bubbles. So this equation describing the radial oscillation of bubble in liquid. So the first term is for acceleration, radial acceleration of the bubble, then pressure, Laplace pressure, viscosity, and the term which describes the compressibility of a liquid. So our theory predicts somehow this plot of radius of bubble versus time. So you can see on the plot that bubble has very rapid compression at some moments, and also you can see self oscillations of the bubble. We will return to them later. So predictions of our model is that assuming adiabatic compression, the maximum temperature of bubble is around 10,000 kelvins. Also, it predicts then when adiabatic index is when adiabatic index increases, then the maximum temperature of bubble also increases. And also, if the temperature of water increases, then the partial pressure of water vapors increases, and the adiabatic index is going down, so the maximum temperature is going down, and the light will be not so bright.
Okay, so we used the following experimental setup. We used a round bottom flask with two transducers glued to the sides of the flask, and one transducer used as microphone glued to the bottom of the flask. We choose the loosest grip to hold the flask because the flask was resonating with the of water in it, so it was important to hold it as loose as we can. Also, as our theory predicts, the effect should be much stronger and light should be brighter on low temperature. So we used ice to cool the flask. Also, it turned out that it was nearly impossible to achieve the effect on just water. We need to degas it by boiling. So we also put lens and spectrometer hoping to get the spectrum of the light. However, we couldn't register it. So this is the electronics schematics. We amplified the signal from generator and used resonance in LC contra to amplify the amplitude even more. The usual frequency was around 27 kilohertz. So it turned out that there was maximum temperature of water, after which the sonoluminescence couldn't be registered. So we studied the dependence of the temperature on the gasation of water. The only way to measure gasation was count days after we have degassed water, because it stayed in flask and the concentration of gases increased over time. So we can see we get the dependence shown on this plot. It correlates with our predictions that So also we were registering the amplitude from a microphone on the oscilloscope, and it turned out that there is a maximum amplitude and minimum amplitude for the sonoluminescence to occur. And we also studied this interval of amplitudes. It was observed that the absolute value of amplitude depends on how precise we can tune into the resonance frequency of the flask. So we considered plotting not the absolute but relative width of this interval. So our theory, it can be seen that there is that there is some dependence on temperature. For low temperatures, it seems to be increasing, and for high temperatures, it seems to be decreasing. So also for this data set, on 16 degrees of Celsius, the sonoluminescence wasn't registered at all with all amplitudes. However, if we lower the frequency from the resonance frequency, something like 50 Hz, sonoluminescence was registered once again. This is phenomena, and we don't know why this happens, but it's interesting. So also, we investigated, we were monitoring on a oscilloscope in XY mode with drive signal on X channel and microphone signal on Y channel, and we observed these pictures when after injecting the bubble, and when the sonoluminescence and when we drive amplitude to high, this sonoluminescence disappeared. The ripples also disappeared. So we think that these ripples are connected with appearance and motion of bubble. So it can be seen that they can be pure, they can be nearly pure sine, and they can be just some oscillations on the. So the number is around 10. So they were proposed a shock wave explanation of this phenomena by Stier. We also proposed that it can be bubble self-oscillation seen on the graph. So there are several points for field research and improvements: is measure spectrum, bubble radius, and so on. Also to control precise gases and investigate phenomena which we registered. So in conclusion, we have registered the phenomena. The conditions for occurrence effect were studied. theory was qualitatively confirmed by experiment, and we found two phenomena of ripples and glow out of resonance.
Thank you.
Thank you.
Now the opponent may start.